Hi, this is Tiffany Martin with Medical Microbiology, and we are in Chapter 6, Microbial Growth and Nutrition. We've been working through physical requirements for growth, and we are up to water. So let's do water. Okay, so water, all microbes require water to undergo metabolism, right? Do you remember that in chapter 5? Water was necessary for cellular respiration. So water is pretty important. So we need to talk about the effects of water and review some things. So hypotonic, hypertonic, these are things you should have learned. If a cell is in a hypotonic environment, what does that mean versus a hypertonic? And so I drew some pictures on my board. Hypotonic means that there are more solutes inside of a cell than outside of a cell. So the environment is hypotonic to the cell, more solutes inside than outside. Water is something that can easily pass through membranes. So when there's more solutes inside, what ends up happening is the water ends up rushing inside of the cell to bind to the solutes, and that's just what happens. So in a eukaryotic cell, in a hypotonic, it's going to get bigger, hippo, some of you remember it that way. The cell is going to enlarge because all that water is rushing in. In a eukaryotic cell, it's going to burst to life. In a prokaryotic cell, remember we've got the cell wall. So there's some protection. Remember my ball and the balloon, and when I blow the balloon up, that water. So there is some protection. So we've got the prokaryotes, the bacteria have a little bit more protection against osmotic forces than a eukaryotic cell with just its cell membrane. So that's good, especially because they're out in the environment. In a hypertonic environment, the opposite happens. More solutes outside. Maybe this is fish and you're salting the fish and you use a lot of salt on the fish to help preserve it. You're preserving it because all the water is now rushing outside of the cell. Microorganisms need that water to grow and you're taking it away. And so salting foods is a method of preserving it. Salting fish, salting meats. So the water is rushing out. So some vocabulary terms you need to know in regards to prokaryotes of that. When the cell membrane in a hypotonic environment is pushing against the cell wall, that is defined as Turgor pressure. So that's a vocabulary term. When the cell membrane is shrinking because the water is being removed, so it's shrinking away from the cell wall, this is called crenation. And this is going to come up when we start talking about staining and capsule stainings, and you can see how that's affected. So again, learn those vocabulary terms for that. Okay, so let me see if I got it all. Turgor pressure in a hypotonic solution, the pressure against the cell membrane because the water is rushing in, no lysis due to the cell wall. Crenation, the cell membrane shrinks away from that due to fluid loss. And we talked about how salting preservation methods can be dependent on this osmotic pressure. And we'll talk about that in another chapter as well. All right, so classification based on different water things. There are obligate halophiles. Halo means the salt, so are adapted for growth. Obligate halophiles require a high salt concentration. Most microorganisms can't take too much salt, and you saw why. All the water gets out of their cells. But there are some that have adapted to a higher salt environment, and these are obligate halophiles. They have to have this high salt environment. There are other organisms that are facultative. Remember facultative, take it or leave it. They don't have to have a high salt environment, but they can tolerate them. One of these examples is Staphylococcus aureus. It can tolerate a high salt environment. And it's one of the microorganisms that live on our skin. We have staph. That lives on our skin. Doesn't cause a problem on our skin. It's adapted to live in this environment where most microorganisms can't grow. A high salt, our sweat that contains that salt, is one of our defense mechanisms against microorganisms that are trying to get in. But Staphylococcus aureus can live in that. So we have a lot of staph growing on our skin. Not a problem on our skin, but if you get a cut, and that staphylococcus on your skin penetrates into your bloodstream and into your tissues, then you can potentially have a staph infection. If your immune system inside your body can't get rid of them quick enough, the staph bacteria can multiply and lead to an infection, and you get a staph infection. All right, so that's an example of that. What else when we're talking about water? If we're talking about hydrostatic pressure, we're going to talk about water pressure. Now, water pressure, anybody, my scuba divers, anybody? I don't think anybody told me that they were scuba divers. If you've ever done that, if you dive deep and under the water, there's a lot of extra water pressure, and that can be a problem on deep dives, and depends on how quickly you can acclimate to that pressure. And that's why divers who have to ascend in an emergency situation very quickly can have problems because of that adjustment to that pressure. So there are organisms that are adapted to this high pressure environment. Barophile is an organism that lives in extreme depths in the sea, and they are adapted to live under those extreme pressure situations. Now, because of that, they have some extra bonding in their proteins. Again, that'll help those proteins keep their shape even in those deep depths. So barophiles are organisms that are adapted to high pressure. Barometer, a barometer measures the air pressure, right? Measures pressure. So barophiles, barometer, pressure. That's your clue on that one. Okay, that brings us to the end of physical requirements, and the next section will be biofilms. Thanks so much.